So as you can see, K-Slit, this is what we were doing in our last classes. This is fourth class. Is it clear? I mean, all of you can listen to me and visibility is also clear. Any issues? May I proceed? Someone unmute.
Sorry, sir, can you please repeat the question?
I'm saying that I'm audible, screen is visible, I'm sharing fitness first.
Yes, sir.
Okay. Okay. So I'll show you what we have discussed in last class or classes rather. We were handling this caselet, fitness first. We had this data of weight, height, and age, and we were interested in making some relationship between weight and height and age. So weight was the dependent variable, and height and age were the independent variable. And we were doing some discussion that the data would have been collected from healthy people. So we are trying to find out if somebody has certain height and certain age, then what will be the ideal weight? That is the purpose of this caselet, and this is what we are doing. To do that, I have discussed with you that there should be I suggested that a template should be used to present and record and report the information of regression analysis. I said there should be three things. First was descriptive, second was regression results, and third we had the discussion on output. So if I'm just showing this just to recall so that you can recall what we have discussed. So this is the descriptive statistics which we have prepared already. It has correlation matrix between the three variables which we have used in our caselet. And here when we are making correlation matrix, we are not bothering about dependent or independent variable. All the three variable would have been taken and their correlation coefficient would have been estimated, and we have done this. In addition to that, two more statistics, mean and standard deviation, have also been calculated and reported in descriptive statistics table. If there are more than two variables, I mean more than two independent variables, we could add rows and we can extend it to that number of rows as per our number of independent variables. So that is what we have discussed. And then second, we moved on doing little bit on regression analysis, and we have, if you recall, we have discussed that there should be 5 hits in reporting of the output of regression analysis, and we were partly doing the coefficient analysis. So still we have to complete the model interpretation, diagnostic testing, parametric stability, and prediction or prediction range. So this yellow portion is something which we have done so far. We have run the regression. I'll do it again for you. I'll show you that I have already imported the Excel sheet here. These are the three variables. CL number can be ignored. And then I run regression. REG is the command. And then I'm supposed to write the dependent variable first, followed by independent variables. Enter. And I've got these. So these three things, as you are finding, coefficients. In this table, coefficients are reported. These three coefficients are reported in this table. And then we also reported standard error. I discussed that the error in measurement of coefficients can be termed as standard error. This is enough at this point of time. And then I discussed that we are supposed to report the t statistics, which is here. And then we have also discussed at length that we have to find out where the p-values are, and you will easily be able to identify where the p-values are. So these are the p-values, and we have just reported all these 4 columns, like this. These are the 4 columns. Today we'll fill this also, and remaining portion we'll try to fill. And we also discussed that statistical meaning of coefficients. Constant has got no relationship with the significance. We are supposed to take constant as it is because constant plays many more roles So whether it is significant or insignificant, that's not going to make any difference in the regression analysis, because constant role is much beyond what it would be, whether it is significant or whether it is not significant. So constant is something which we have to take all the way. So that's why we are not discussing whether it is significant or not. At least at this juncture, it is not. It is not required. Then all the coefficients of height. Height has got coefficient 0.72732, 0.73. We have rounded it off. And then we have discussed that significance means if p-value is less than 0.05, we discussed that we will be using this pair of hypothesis. This is a very generic hypothesis for coefficient in a regression analysis. Whenever you have got regression analysis, you can use this hypothesis. This is the null hypothesis, which is generic, which can be used all the time whenever you are doing any study of regression analysis for any coefficient. And we have discussed if p-value is less than 0.05, we are supposed to reject the null. And as we are finding in this, p-value is for a coefficient of height, p-value is 0.01, which is obviously less than 0.05. So we are supposed to reject the null. So we will be not exactly, I mean, we cannot reject the null. Right now we are rejecting the null. So we will say that we are accepting the alternate hypothesis. We'll say that the null of 0 is rejected. So we'll assume that the coefficient of height is statistically not equal to 0 or it is significant. So if null is rejected here, it means null of coefficient equal to 0 is rejected. Alternate, which is not equal, coefficient is not equal to 0, is accepted. And we'll say here height coefficient is statistically significant. The case is exactly opposite when we look at the coefficient of age. P-value is 0.221, which is obviously not less than 0.05. So we will say the concluding argument here is that we will say that the coefficient of age cannot, the null related to coefficient of age cannot be rejected because p-value is not less than 0.05. When null cannot be rejected in case of coefficient of age, it means we have to consider that the coefficient, although it is mathematically not equal to 0, but we'll consider statistically the coefficient of age is coming out to be 0. So this much discussion we have done. So this age point minus 0.26, though it is mathematically there minus 0.26, but statistically because p-value is less than 0.05, null of coefficient equal to 0 cannot be rejected, so we'll assume it is statistically equal to 0. All these points we have reported in the discussion of output. This template is supposed to be filled in detail. This is something what we are reporting. So practically, if you follow my discussion, whenever we are doing a statistical analysis, we are supposed to complete these three things. We should have one table on descriptives, another table on regression, and third discussion like this should be done. We'll be completing the remaining portion. What we have done so far. Now we're going to start the new thing. Any question, any follow-up question or anything which you are not clear? Yes. Anyone? Anyone has got any issue?
No, sir.
Okay. So, as you look at this regression analysis template, second table, we are having one more column which is not filled, which is standard coefficient. Please understand the difference between unstandard and standard coefficients. The purpose of standard coefficient is that we would like to know the comparison. as we are saying that we have got two, beta 1 and beta 2, because our regression equation is beta 0 plus beta 1 x1 plus beta 2 x2. So here what we are finding, we are having two coefficients, beta 1 and beta 2. As you have seen here also, we have got height and age. So height can be considered as the coefficient of height as beta 1 and coefficient of age is minus 0.26. Now question is, right now there is a slight problem that we do not have both as significant. One is significant, other is not significant. Despite that, we are supposed to have this discussion that which is more important? Importance between beta 1 and beta 2. If there were more, then again we would have said which is most important. Important in predicting the value of y. So when we are having a regression model, we would like to know whether x1 is more important or x2. When we say, when we want to know whether x1 or x2, this can be done with the help of comparing beta 1 and beta 2, and this comparison is done with the help of standardized coefficients. So standardized coefficients help in understanding among the used independent variables which are more important. So their relative importance can be estimated with the help of a standardized coefficient, and their absolute value is seen. Higher the absolute value of standard coefficient, the importance of that particular coefficient or that the variable, independent variable attached to that coefficient will be relatively more important. I'll show you how we practically do. First of all, I'll show it on this Stata. Everything will remain same. We have to just put one comma and we'll write beta. No difference. We will just write additional thing. I repeat myself, this is the command which we are writing. I have just added comma beta in the previous command. Previous command was regression, weight, height and age. Dependent variable followed by independent variable. What I am saying, new thing, put a comma and write beta. And as we run, what we are finding, we are getting one more column beta. So this beta is nothing but the standardized coefficient. I repeat, this beta is nothing but the standardized coefficient. So I can jot down the value of this. This is, though you are finding it is similar, but don't worry. Always, this may be a coincidence. It is not going to happen all the time that you will have similar values. So right now, whatever is coming, we are supposed to report. We'll report 0.73 for height, 0.73 for height, and for age, we are having the beta, the standardized coefficient minus 0.28. Minus 0.28. So if you look at the absolute value, obviously, the significance discussion is on one side, that is there. This is another discussion out of height and age. Height is supposed to be more important because height is having more absolute value, that is 0.73. So height coefficient, standardized coefficient is higher in value in absolute sense. So height is more important than the age in contributing the prediction power of dependent variable. In this case, it is weight. So weight can be more influenced by change in height as compared to change in age. That can with certainty be established with the help of standardized coefficients. Point is clear? I believe we'll have two-way communication. Feel free.
Yes.
The point is clear?
Sir, could you just show us the formula once again? Just the
Formula is nothing but we have just, this is the normal command. I put one comma and I'm writing beta.
Okay, sir. Yeah.
Enter. I've got the same thing. I'll show you in regression this eViews also. Let me work file, unstructured, undated. I've got 10 observations in this caselet. So I'm putting it undated, unstructured, observations 10. Okay. This has come. I've gone to empty series. I'm going to Excel, copying everything, including the name of the field, and I'm just putting it here and taking the cursor one step ahead, and that's it. Closing it, delete, everything is here. All three variables which I have copied from Excel is here. Right now I need to go for estimating equation. Here I have to write, it's like weight. For constant I have to write C. The commands are different in EViews as compared to Stata. HT will have and then age. So that's it. Same output we have got. And if we want the standardized coefficients, then you can note down the path after running the regression. Please pay attention. Go to view, coefficient diagnostic, scaled coefficient. You note down wherever you are noting. As we click this, and here we have got standardized coefficients, you will find that these are the unstandardized, these are standardized. That is available. If you notice, we have got the same values, what we have reported in our regression table, table 2. Yeah, all of you are with me?
Yes, sir.
So if I come back to my regression, so this is the new picture, and constant has got no meaning because we are finding out the relative importance of independent variables. So this is what we have. VI will be calculating later on, most probably today. So with this, we are closing the coefficient analysis. If I complete this discussion, coefficient's relative importance will say height is more important than age, because standardized coefficient of height is more than age. So we are supposed to write this. There's nothing wrong in writing the details. It is helpful for you as well as it is helpful for those who are going to understand your work, because why will you will be doing any analysis? You are supposed to report to somebody. So wherever you are going to report, you are supposed to write these things in detail. And these things are not too much, not too less, neither too much, not too less. It is somewhere what it should be. It is appropriate. This much discussion of output of regression analysis is appropriate. It is neither more nor less. So with this, what we are finding that we have completed coefficient analysis. Now we are moving to next part of 5-point summary of output of regression result. We are moving to model interpretation. This is second stage. Coefficient discussion we have done at 2 levels, significance of individual coefficients, and we have also estimated the relative importance, and we have estimated standardized coefficients. So unstandardized, standardized, and if I have to write down the model, that model I have also written, so that model is also there. If you remember, we have written the model somewhere. Yeah, this is the model. Practically, this is the model which we have estimated, and we have done the individual coefficients, standardized as well as unstandardized discussion. So that's 4. We are moving to understand the whole model. Now we will not be looking at parts. So discussion in bits and pieces are over. Now we are going to have a cumulative, holistic discussion on the whole model. Right now I'm having only 2. I might have 4, 5, 6. So any number of independent variable can be there in my regression model. Right now, when we do the model interpretation, then the holistic approach will be there and the whole model will be discussed. If I show you, there are 3 things: R square, F test, and SE of regression. We also call it standard error of regression. So we'll take first thing first. We'll start with R square. We need to understand R square. R square, a value If you look at here, you are finding on the right side R squared is 0.71, and we have got one more thing, adjusted R square. So we need to understand what do you mean by when we say R square. R square is the ability of the model to explain the variance. Let me repeat. When I say explain the variance, it means y is something. Y means dependent variable. We are trying to build a model for y. What is the model? Model is for y. Model is for weight. So our whole attention is obviously for weight. So what we are saying, R square is something which tells up to what extent we can explain the variation in weight with the help of these two independent variables. So obviously, higher the value of R square, better the model, or rather it is much more appropriate to say fitness of model is better. What do you mean by fitness? Up to what extent independent variables can explain the variance in dependent variable. I repeat, up to what extent independent variables used in the model can explain the variance in dependent variable. If I have to explain, then I don't want to use these statistics here. Just understand this much. Just this much is enough for you to understand R square. The value of R square is calculated in percentage. So 0 to 100% is the range. 0 to 100% is the range. Higher is better. If the value is 0.7, I think 71 is coming here, 71.24. So we'll say 71.24, 7124 or 71.24%. So right now, the fitness of my model, I repeat, fitness of my model is 71.24%. So in a normal way, we'll say higher the value of R square, more fit the model. Fitness of the model can be mathematically estimated with the help of R square. But there's a problem with R square, that R square might be having issues related with number of independent variables. When you have more number of independent variables, the value of R square by default may go up. But if you remember my discussions earlier, we have talked that there is a rule of parsimony. The rule of parsimony is very clear that the number of variables which we are supposed to use in any regression model should not be neither too many nor too less, somewhere in between. Or lesser is better. If you can get the similar result by using lesser number of independent variable, then that type of model will be preferred. Keeping that in mind, R square may give us misleading interpretation, because R square is straightaway high if we have more number of independent variables. So that may lead that may create some trouble in interpretation of R square as a tool to measure the fitness of model. That's why we use adjusted R square. When we say adjusted R square, it removes the negative impression of higher number of independent variable in the model, and adjusted R square make the estimation of model fitness neutral with respect to number of independent variables used in the model. So this neutralization process of R square is done with the help of adjusted R square. So we can conclude that we can report both. R square should obviously be reported, but it is also important to report R square, adjusted R square. So adjusted R square is seen with the help of putting a bar on the R square. It becomes, usually this is the notation which we use. So the first tool in the discussion of model interpretation is R square. And here, as we are finding, you can report both. I'm not saying you report only, you'll say R square is 71 point, we are at 71.24%, and adjusted R square is whatever it is, will report this is 63.02%. So usually when we are interpreting the model, we surely talk about adjusted R square or R square, and higher the value of R square, we will consider model is better. But there is a caution. When we are doing behavioral studies, all the time you won't expect very high R square. So that depends what type of study you are doing. So in some behavioral study where you are doing some psychology based study or consumer behavior type study, then at times 30-40% of R square or just R square is also considered good. So R square should not be seen in isolation, rather that depends. The value of higher R square or acceptable admissible value of R square is also relative. That depends on the case what you are studying. So in absolute way, saying that higher R square is good, that's okay. But you have to relatively also look at what exactly you are studying. And if the studies are behavioral or some studies where high R square is very remote, so we have to manage with the lower values of R square. But within 2-3 models, suppose you are testing, so higher the value of within those, higher means let's say you are running 3 models. One is giving you R square 45%, other is giving 40%, other is giving 35%. So obviously within these three, you will say the model which is giving 45% of R square is supposed to be considered for further analysis. So that's okay. But all the time expecting very high R square is something which is practically neither possible nor advisable. I hope this R square discussion is clear. R square is a very important discussion, a very important thing. You quite often people discuss R square thing whenever they are running any regression model. May I proceed?
Yes, sir. Yes.
Sir, I have a query.
Please go ahead.
You said that R square for it varies from 0 to 100. So
Correct.
100 R square of value of 100 would be a theoretical idea, right? Means it might not, you might not observe it in practice. Only in it's just a theoretical number. There wouldn't be a real life example of a
No,
perfect
no,
model in which all
100% is
variables are.
not possible. There is
Yeah, yeah.
no 100% from sample data, even from population data, it will not be possible. So having the 100% R square is something which is not possible.
Okay. And I have another question. Now, if I'm like doing any preparing any model for any research purpose to in order to understand some variable. So if I get an R square value, then wouldn't I likely compare it with the R square value which is obtained by other researchers or other models in order to compare my
Perfectly,
model?
perfectly. That should be done.
Okay, okay.
And I mean, one more important thing that it is comparable. R square is just because it is measured in terms of percentages, so it is comparable. Somebody has got 70%, you are getting 65%, then obviously it can be compared straight away without any problem. So R square is good. It is popular because it is comparable.
So wouldn't the interpretation be that the other model which is having a higher R square is a better model than my
In a
model?
way, but again, you have got the whole 5 point of discussion. So one thing is obviously R square is high, but doesn't mean that if you are having a model which is better on other parameters, so absolutely you cannot say your model is poor. I mean, it's not that R square is so important that if it is inferior, then the whole model is inferior. No, the whole model has to be seen in totality.
Okay, okay. I
So
cannot
saying which
I
is
cannot
good
judge a model
is ha
on the
you
basis of
know
only
just
one
by
parameter.
one parameter. Yeah. A cog in the wheel. It's not the whole wheel. That's
Okay,
something which you have to take care.
okay, okay. Thank you, sir.
I'm open to question. I appreciate if you ask. So we are moving towards. So we have done this R square discussion, and please pay attention. I'm reporting it in detail. After maybe next discussion, next class, you will have your first assessment. So I'll give you one regression analysis problem individually to all of you, and you have to prepare all three things: two tables and this detailed report, and a few more things which you have to send it to me. As the output of your assessment. So please take care. that you have to elaborate what you have found. So your mathematics or statistics is on one side, discussion is more important because this is what the user of the model is going to read, going to look at. What you have done, you have to justify, give justification, explanation in the report. So report is going to be equally important. You will be judged on the basis of report. Calculation, what you have done, that you know. Because the user will look at the report. So you have to take care of the report part. It's not only for your examination or your assessment, it is in real life also very important that it should be properly reported. All the things which should be reported should be there. So you need to be conservative. You may have one or two extra information, that's nothing wrong, but something which should be reported and that has not been reported, then that might create trouble in terms of the sanctity of your output or your work. So you have to be very careful when you make a report of regression analysis. So if you just take care of these 5 points, I think that around all the important parts would have been taken care of. So our standard would have already been achieved. Coming to next point of model interpretation, F-test. If you look at the output, F-test, as you are finding it here, please pay attention, F-test. And as you are finding that F-test is having accompanying p-value. This is the p-value for F-test. And let me put it this way. Again, I'm writing the null. Please pay attention. Whenever we are doing any testing of significance or testing of hypothesis, I should surely write what is the null. So when I'm saying that I'm going to discuss about the F-test of model, F-test of the regression model. In that case, the null is model is not good. You remember I've discussed that the null is either no difference or no association. So this is again null of no difference. So model is not good means not, it's as good as beta 1 is equal to 0. That type of null is there. I'm just writing it differently so that it can be easily understandable for you. But logic remains same. Null has to be of two types only. Either it would be no difference or no association. So this null comes in the category of no difference. So model is okay. So this is the pair of hypothesis which we have for F-test of regression model. Please pay attention. We are talking about F-test of model. F-test is going to be used at different places. So where, what, that depends. So right now we are having one F-test for model, regression model. So we are just using this. Look at this. What we are finding, the value of F-test is 0.8, 0.67, and corresponding p-value is more meaningful. This is 0.0128. So the F-test value is 8.67 and corresponding p-value is I can write down that p-value in bracket 0.012. 0.012. My next question. This is p-value. Class, please tell me this p-value is more than 0.05 or less than 0.05?
More than 0.05.
Correct, come on, 0.01. Is it less than 0.05 or more than 0.05?
Less than.
Less.
Take your own
Less
time.
than point.
No hurry. Take your own time. 0.012 is, we have got 0.050. Is it less? Is it less or more? Yes?
Less.
Less. All of you are on the same page. No confusion. 0.012 is less than 0.050. If you multiply it by 100, let's say I'm multiplying both, so it is coming out to be 5.0. It is coming out to be 1.2. So obviously 0.05 is more than 0.012. So this look at the p-value. So p-value is less than 0.05 as you are finding it here. This is the p-value. which is less than 0.05. So 0.05 is more than the p-value of the model. So p-value is less than 0.05. Simple. So if p-value is less than 0.05, my interpretation is reject the null. And following that logic, I'll say reject the null means reject the null and accept the alternate. So I'll say my model is okay. Why? Because corresponding p-value is less than 0.05. Null that model is not good is rejected. Alternate that model is okay is accepted. Class, you're with me?
Yes, sir.
So,
Yes, sir.
anyone has got even out of confusion, please raise your voice, raise your hand. I mean, in a way, just react. Don't hold yourself back, just speak up. If you have any problem, if you are not clear, even if I have to repeat it 2-3 times, don't worry. Worry for you. You are the most important person individually. If you are not clear, please ask.
Sir, could you please repeat that example 0.50?
You know, this, look at here, this is 0.0128 is the corresponding p-value of this f-test. Right?
Yes, sir. Yes, sir.
This you can figure out.
Yes, I can.
Then we have given you one, you know, this is going to be used in the whole, I mean, the statistics is this only, whether statistics, econometrics, wherever you are doing any testing of significance across the board. Because whenever you are using a software, that will give you p-value. So whether you are doing anything in data sciences or statistics or econometrics, this is going to be the rule. If p-value is less than 0.05, this 0.05 is subject to change. We have different discussion. It may be 0.01, it may be 0.1, but we go always midway, preferred way. So I'm sticking to it. So p-value is less than 0.05 means reject the null. This is a bold statement, can be applied everywhere. Keeping this in mind, we will compare the p-value which we have calculated or we have found in our F statistics. And what we are finding, this p-value to the corresponding F-test is 0.0128. And we are very clear that 0.01, rounded off, it will become 0.01. It is less than 0.05. 0.05 is high and 0.01 is less. So keeping this in mind, p-value is less than 0.05, 0.012 is less than 0.05, we are supposed to reject the null. And to complete the discussion or argument, I have to look at the pair of hypotheses. The pair of hypotheses where null is, model is not good. I mean, as we have understood, just because p-value is less than 0.05, null is to be rejected. So we have to reject the null, accept the alternate. It means null that model is not good is rejected. And we are accepting the alternate hypothesis, which is model is equal. Okay, so we are just concluding using this hypothesis testing that model is okay. Vaibhav.
Yes, I got it. Thanks, sir.
Got it? So we have to just look at and use your presence of mind. Look at the p-value. P-value, if it is less than 0.05, reject the null. That's it. Don't remember anything else. Otherwise, you will be having so many things to remember. Just remember this one liner. If p-value is less than 0.05, reject the null. Yeah, somebody was trying to say something. Okay. So we are coming back to, you know, when you don't say I have no other choice but to accept that everything is okay. And later on, if you have query, that's not great. Don't worry for anything, worry for you. I'm repeatedly telling you, if you are not clear, just ask. Don't worry for me, worry for you. You are the individually most important person. then I'm having a class. Fair enough. So we are just concluding here. We are saying f test. Right now we'll write the value. F test. Um, as I have written here, 0.867, 0.012, 8.67 f test is significant. Language is significant means it is meaningful. P value is 0.012 and 0.0 or no, let me get the value 0.028. 0.028 f test significant because P value is less than 5% or less than 0.05. This much. I'll add one more line here. The F test is significant at 5% level of significance. 5% level of, I'll explain the new line, significant. So I've added this line. This line is nothing but same thing. 0.05 is nothing, 5%. I have to use certain language which is acceptable in the statistical world. I'm writing that f test is significant at 5% level of significance because my comparison is with 0.05. That's why I'm writing 5% level of significance. If I change later on at some point of time, then I will give you again a brief how to write and why I'm changing. But right now, this is enough. Just because you are comparing the p-value with 0.05, you can add this. The F test is significant at 5% level of significance. This is the right way to write the whole thing. Even if you don't write this additional line, nothing will be wrong. But if you write, then you are making your work look much better. You're with me?
Yes, sir.
So we have completed this. Now we are at the third part of the model interpretation, that is SE of regression. SE stands for standard error of regression. What happened? If you remember, we were talking when we were using this. Right now also I need to report it here, 8.67, and in bracket I can write down 108. This is the normal convention, and I can, I can write in p-value is reported. I'm just noting down in the table, note of the table, p value is reported in brackets, parenthesis. So this is the style to write. So it is clear whenever you are having any parenthesis or small bracket, that is obvious interpretation that is p value. And f test, so obviously this is going to be the f test. So this much representation we can do. R square we need to report. R square value was how much? It was 63.02, 63.02, or we can, if you want to report both, we can report both also, or you want, just because I've written adjusted, you can survive with the adjusted R square. Or you want to be more perfect, then you can write down R square is 71.24, 71.24%. That's it. So this much portion is also done in the, we are reporting in table as well. And we are also having discussions. Yeah. So I was talking about SE. When when I was discussing, I said standard error. This error estimation is nothing. Standard error is the error in estimation of these coefficients. But it is not relative. It is absolute. So it can't be compared as such. But higher the value usually whenever you are having two, and then you are supposed to class में हूँ क्लास में हूँ। हाँ दे दो, अपने कार्ड से दे दो, कैश दे दो यार, क्या मैं क्लास में हूँ। Hello, sorry. So we are standard error. So standard error, this is the error which is error in measuring the coefficients. Similarly, when we talk about the whole model, then this item SE of regression is error in estimating the whole model. So if you look at here, this root MSE, mean, this is also known as square root of MSE, mean squared error. MSE stands for mean squared error. So practically this is nothing but the standard error of regression. SER we also call it, root MSE also we call it. What we call it, that's less important. Where it is to be captured and where it is to be reported and what is the interpretation, these things are important. So when it comes to capturing the standard error of model or a standard error of regression, this is the place where it is reported, and you are supposed to take it and put it here, 6.04, 6.04, that's it. And it is not relative. So if two running models are there, then you can compare. Otherwise, as such, it is nothing a big thing. But it should be reported because people say that it should be reported. It gives you at least some feel that what is the value of SE of the model. So like we are reporting this, we are supposed to report this also, standard error of regression. Dash, with me?
Yes, sir.
Sir, I have query.
Please go ahead.
The standard error of regression is this same as the standard error of mean, right? But if I'm not wrong, standard error is there for separate variables. Means this variable height will have a standard error, the variable age will have a standard error, and here we're talking about standard error for a model itself. So how did you get that?
No, how did I get that means, do you want to understand the concept or the mathematical value?
Maybe we can just understand first the concept.
So concept understanding, I'll give you clarity on that. You know, when we are running a model, so we are, if you remember, we are making use of some sort of distribution we are using, you know, distribution. So when we are saying that we are using distribution, then optimum least square is a method which we are using. And if you remember, we have discussed in some point of time in OLS, we try to reduce this gap, y minus y cap. Y cap is the estimated value. We call it u cap. Can you follow this much? This is the value of sample data. This is the value which we can calculate with the help of model, estimated value. So there is usually a difference. If you remember, let me show you so that I can answer your question. Look at this. We have made this, you remember, this U? Can you
Yes, sir.
recall?
Yes,
So when
yes.
we are having OLS regression, then what we are trying to do, we are trying to reduce this. Understand?
Yes,
So
sir.
when we are trying
Basically,
to
we were
reduce
trying to find the line of best fit
line
in a
of best
scatter
fit,
plot.
perfectly. That is the idea. So what happened in that case? When we are trying to find out the line of best fit, then we have to calculate the value of beta. So beta value can be calculated. Beta 0, beta 1, beta 2 can be calculated by applying differential calculus here. We used minima maxima concept on differential calculus. You understand? You are an engineer?
I'm a CA, but I understood that
You understand differential
that
calculus.
we can use the
One
derivative.
tool in mathematics which is there, which can be used for calculating minima maxima points. So just because our job is to reduce this, so we'll find out the minima, the point where this is reduced, minimized. So that value will give me the coefficient value. So coefficient values are easy to calculate with the help of this concept. But when we have to find out whether it is equal to 0 or not, we have to advance our concept and we have to go for testing of significance. So when we have to go for testing of significance, then we have to calculate the value of SE for coefficients. SE standard error value for the coefficients. So in a way, you can say that is very well coming from the standard, roughly this is the under root, So there are a few formulas which I don't often remember. So roughly you can understand that sigma by under root n can be one of the understanding if you have a background of statistics. So when we are having a sampling distribution of sample means, then this becomes the standard error. I hope, are you getting this?
Yes, sir. I know this formula also.
This formula you
Sigma
understand?
upon sigma upon square root of n.
So this is in a way standard error of sampling distribution of sample means. So partly what is happening, if you remember my discussion, I have told you that the coefficient divided by SE will give me a value of T. And why I'm calculating value of T? Because I'm interested in finding out whether it is significant or not. So if you follow my discussion right now, what I have told to you, that to estimate the value of beta 0, beta 1, I can use this concept of OLS. But to know whether it is statistically significant or not, I have to go for, again, distribution, concept of distribution. So I have to calculate the T distribution, or I have to calculate T statistics. So when I have to calculate T statistics, I have to have the concept of coefficient, roughly I can say coefficient divided by SE. So that will give me one value which is tabulated value, calculated value, which I'll be calculating, comparing. This is calculated value, and I will be comparing this with the help of tabulated value. So here, when I say roughly 1.96 in extreme cases when the sample size is pretty big, so I'll compare. So what is happening that T I need to calculate so that I can test whether statistically the value of coefficient is significant or not. So to do that, I need to calculate SE. Taking this analogy further for model testing, I need to estimate the value of error which is found in estimating the whole model. So in a way, the way I have calculated a standard error of sampling distribution, which is meant for only a particular coefficient, I need to calculate the standard error to test the whole model. So right now I'm replacing this concept from coefficient to a model. So when I move on with this concept of SE for a coefficient to SE of a model, then this is the value which is estimated for calculating the SE of the model. I hope I've partly answered you.
Yes, sir.
So standard error helps in identifying whether the model is appropriate or not, keeping the F test in mind. Or we just casually we can say that this standard error of regression is the estimation error. When you are estimating the, like we are saying, a standard error of coefficient gives you error in estimating the coefficient. Similarly, when we are making the whole model, then what is the cumulative error that can be represented with a value which is known as standard error of model. If I show this here, right now I don't have an OR table actually. Both no, here I have an OR table. Yeah. Look at here. Here when we are getting the F statistics, so this F statistics can be calculated. This interpretation. If I'm not wrong, you calculate the under root of this value, you will find, I think this is coming out with this. Calculate, this is coming. Yeah, it should be partly closed. Yeah. Are you with me? That's why we are calling it mean square root of MSE. This is mean square. This is the sum of squares of explained, sum of squared of error. We divided by their respective degrees of freedom. We get to know mean, sum of squared. And if you calculate the under root of this, you will find that root MSE is here. I'll suggest that we need not go into that detail, at least here. Is this much enough?
Yes, sir, it's fine.
So if I precisely answer your question, the SE of regression is going to estimate the error present in the estimation of the model. You have any follow-up question? I'm open so that I can, in a brief, I can answer that also. I'm waiting.
Sir, as of now, I don't have any query, but I will also do research on this independently. And if I have any query in the future, I will definitely ask you.
You can meet me offline also. You can, if you don't have my number, you can take it from CR and you can, talk to me. No problem. Right?
Yes, sir.
Oh. Yeah. DF test SE of regression. So we'll report SE of regression. This is 6.041, 6.0431 is the value of standard error of regression. Yeah. So here we have got the value. So this is complete our discussion on model interpretation. So we have discussed three things: R square, F test of model, and standard error of regression. All these three things are reported under the model interpretation. So we have completed the coefficient analysis. We have completed the model interpretation. We are moving towards diagnostic testing, which is slightly difficult part, but will survive. No problem. If you have understood so far, you will be able to understand next discussion also. I'm open to questions. I believe some of you might be having some questions. Please don't hesitate and ask. Done. So we are moving to third level of diagnostic testing. If you recall my discussions, then what we have said that the whole estimation of regression coefficient, everything is done with the help of OLS. And optimum least square, the method which we use in estimating the values of beta 0, beta 1, and beta 2 in this situation, depends on certain set of assumptions. So set of assumptions are very important. And out of set of assumptions, three things we mostly pay attention to, which are relatively more important and can differentiate, can create much trouble. First is known as heteroscedasticity. Heteroscedasticity. Pronunciation is slightly difficult, but gradually will pick up. Heteroscedasticity. Then we also talk about multicollinearity. And third thing is autocorrelation. So normally when we are running regression analysis, we surely have a discussion on these three aspects of diagnostic testing. As you are finding in the template, multicollinearity and autocorrelation are written as optional because that depends on case to case. We'll unfold as we reach there. We'll start with the heteroscedasticity. Heteroscedasticity is an assumption which says that the variance in the, when we are estimating the coefficients or model, we have got something known as U or error term. So error term is very important. If you recall the discussion, then Y is something what we are trying to estimate. Y cap which we would have estimated, and what we have not estimated is U. So this whole thing, this Y minus Y cap was equal to U. I have just put the Y here so that I can make a point. This is the data, with Y I have got X1, X2 in my example of fitness past. And I have estimated Y cap. And ultimately, I am studying the weight variable or the dependent variable. So this is what I was interested in. But when I have estimated, I have only estimated this. This portion has still not been estimated. So I'll call this observed observed part or estimated part, and this portion is called unobserved. We have still not observed this error part. It means when we are running a regression analysis, one part is explained, other part is not explained. So the part which is not explained tells meaningful thing about the use of OLS in estimating this part. So the remaining, the residual portion, or we also call it error term. So error terms tells volume about the observed part, whether this observed part is good, great, or bad, or whatever it is. So when we say diagnostic testing is also done with the U term. And for every, as in our example, we have got sample size 10. So it means when I run the model, I have got Y and X1 and X2, all these values were also there in 10 numbers. If as you have seen that we have got estimated model and we have estimated, so estimated model is written like, this value, what we have got, minus 39 point and 0.73 plus 0.73 height and minus 26 age. That is something which is the model. So what is happening? If I put the values of 10 items of height and age, I will be able to calculate the values of Y cap also from 1 to 10. So it means I not only have the values of Y which is there from 1 to 10, but I have got the Y estimated also value from 1 to 10. So similarly, I'll have the value of error also, this error also, which will be from 1 to 10. So I've got 10 observations of error term also. Class, you're with me? I've got Y, which is actual. I've got Y estimated, which I have estimated with the help of my regression model, which I have estimated. And then if I subtract Y minus Y cap, I will have the value of error. And similarly, I have got values of Y, 10 observations. Y cap will also be 10. Similarly, error will also be giving me 10 observations. Are we together?
Yes, sir.
Yes, sir.
So the assumption of heteroscedasticity says that this error term, the variance of error term, variance is what? All of you have studied the SD, standard deviation, in your start class. I guess Anugamini would have covered this portion so far. Standard deviation, measure of dispersion.
Yes, sir.
So when you square the SD, square of SD is nothing but variance. SD is nothing but sigma, and when you square it, you get to know the variance. Is it okay?
Yes, sir.
So what is said when we talk about heteroscedasticity, that the variance of U cap with respect to, I'm just giving you slight theory, but please bear with me, because without that it would not be appropriate to complete this discussion. With respect to independent variables, I'm putting it xj. J in our case is 1 and 2, should be sigma square, or in a way I'm saying this is constant. Constant. Sigma square I'm writing same thing, notations are looking same, but the basic idea is what I'm trying to tell, that variance of U error term with respect to all the independent variable should be constant. So this is the assumption. Don't go in theory more than this. This is enough at this point of time for you, that error which we are calculating, the variation in error with respect to the independent variable should be constant. And that is the assumption. That is the assumption when we call that assumption of heteroscedasticity, or the right assumption is that the error term should be homoscedastic. So the term homoscedastic is something which we expect, and we are obviously, when it is not there, then the distribution or the model is having heteroscedasticity. Are you with me? I'm talking to something where you will find in books of statistics or econometrics, the whole chapters of 100 pages are there. I'm just trying to give you the gist of the idea so that I can make use of it. I'm not teaching theory, I'm teaching the application of econometrics, and I think that we can do it reasonably well. So our focus, our objective is clear. We are not studying theory, we are studying application of theory. So you are free to ask questions if you are not clear with the concept. Feel free in reacting if you're not clear. Is it clear or it has gone overhead transmission?
No, sir. Yeah.
Clear? So I repeat myself. The assumption of heteroscedasticity says, I've explained to you the way I have got values of x and y, I can calculate the value of y estimated also, which is very easily possible. I think you can calculate it. I can, devote some 2-3 more minutes. I can calculate on Excel. If I just come to me, I can calculate what is the value of 0.39 is the value of beta 0. I'm just trying to build some confidence to you so that you don't understand that things are that difficult. Things are not. This is beta 2. Beta 2. All of you are with me?
Yes, sir.
Yes.
So I'm just trying to make things a little more acceptable to you. This is practically why I'm here writing weight cap. Weight cap. I'm calculating it for you so I can show you the error also. So if I have to run it, I'll calculate this. What is the equation? Equation is this is the constant beta 0 plus this is the beta 1 value, and I'm multiplying it by the values of height. Height is the x1, so coefficient of x1. I hope this is clear.
Yes, sir.
Yes, sir.
And I'm adding one more term here. This multiplying it with the h. And just because I have to keep this constant, the values of this L4, I have to just go for absolute referencing so that when I drag it, this should not, my Excel has got some problem. I think I'll be able to survive. But yeah, this is the value. This is the estimated value. Yeah. So this is the value which I have got by dragging. My dragging option is not working. We use too many things and get trouble. So this is what I have got. If I explain to you, these are, you can, if you are having Excel, you can also check yourself. These are the values of y cap, or right now it is weight cap. So if you look at the function here, yeah, look at here. Look at here. What if I'm showing you what is happening at f3? Then it has taken these two values with the respective values of height and age. It has calculated. Same thing for every time. I made this absolute. Beta 0 is having some issue. Let me. This one more thing is also having. Yeah, this is correct value. So yeah. So these are the values of y cap. Class, you are with me. I'm doing Excel, obviously. I have to, I guess some of you, if having problem in Excel, I can explain quickly. I've just made use of Excel.
Yes, sir.
I believe some of you must be having problem, but right now, just bear with me, because here I'm not teaching you Excel. I'm just trying to explain to you U cap. I'm estimating U cap of the error term, or I call it U cap. And this value, as I said, this is y value. minus y cap, and here I have got all the values of, look at all the values, they are nothing but the subtraction of y, yc4 minus f4, and likewise you have got. So these are the values of u. Are you with me, all of you? So when I
Yes,
say, when I'm talking about error term, so this error term, again, I have to put here, I can't show you, that's not that easily possible to calculate. This term, which I was trying to tell you, this I'm referring to. But right now I have to make it conditional variance. I have to calculate the value of u, but condition to independent variables, these two, condition to. So one time xj, when I'm saying that collectively I'm representing, j means one time x1 and one time x2. So this conditional, so this is the error term. So variance of this condition to independent variable should be constant. So that I can't show you like that, but concept is clear that the conditional variance of error term should be constant. But that need to be tested. Right now, I've taught you the concept that OLS takes this as a concept that there should not be any homoscedasticity. And just to explain what is homoscedasticity, I've explained to you this concept. Now I'll show you how to test this statistically. That's my job. The thing which is left is to prove this statistically, whether this problem is there in my model or not. That is the purpose of diagnostic testing. Concept is clear. Conditional variance of error term should be constant. And to test that, I hope we are clear what we are doing. So when we have used OLS, we have got assumptions. Assumption should hold true. If you have got some results of model beta 0, beta 1, beta 2, and you are saying that you have done good, prove it. So when you communicate this to somebody, you have to test whether usually all these things are to be reported, because these are the way by which we understand the model, whether it is good, bad, or appropriate, or having what are the limitations. So in that very discussion, you will find that this also comes into picture, that you have to do the discussion on diagnostic testing, and diagnostic testing is usually done on these three heads only, and we have to report. If it is not there, report it. If it is there, report it. And if it is there, then how to correct it, that also we'll discuss right now. But we are supposed to report it that there is some heteroscedasticity problem, so we have taken this corrective action, and this is my new output. So that discussion has to be done. Class, with me, we're talking about heteroscedasticity.
yes, sir. Sir, could you please show the Excel sheet once? Sir, do we not calculate the final, as in we got U cap for individual items? Do we not calculate the final value? Should we or
Final
should we
means
not?
what?
As in, we got 10 values, so out of 10 we come up to a single value. Do we do that or we don't
No,
do
no,
that?
no, 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 no. You know,
Okay.
what happened that when we talk about having the OLS model, so what happened that a long mathematical description is there. I can tell you the mathematical formula also, but I don't expect you to remember that complicated formula. Formula, why should I discuss with you? Suppose, or why should I share? Because never ever, because you are not doing a theory course on statistics. You are making use of it. So in your real life, you will never ever do the calculation part of running the differential equation, calculating the values of beta from the formula. You will always have Excel with you to solve the problem. So I won't recommend you to go into that
Sure,
technique.
sir.
But conceptually, you can ask anything, I can explain to you. So U square, we need not calculate. That is calculated, then differential calculus is applied, and then those all things are done with the help of software. Concept, you can ask. Calculation part, I'm not interested that you should go into that depth. That is not definite, that is calculation. Rigmarole of calculation, avoid it, not required. Learn the concept, apply it, and go on. Right?
Sir,
And you need not report this much also, I'm not asked you to report this in your any standard output. Yeah, please go ahead. Question.
Sir, conceptually, please can you explain once more ki heteroscedasticity, like why are we doing this? Like you said ki we take the y bar from the best fit line, and
Hmm.
because we don't observe, like we get u from the difference of y and y bar.
Okay.
So I'm unable to understand like what are the set of assumptions because of which we are doing this. Conceptually, if you can make
No,
me
your
understand.
question is that why we have assumption. This is the concept. This is the question, or you want to understand the concept of heteroscedasticity?
I want to understand first, like, what are the set of assumptions, because I'm unable to understand what are the set of assumptions because of which we are doing this. Like, what is the
Your good
error in
name. Your good
first place?
name. You are
So,
Abbas.
Shrivardhan Daga.
Srivardhan, can we have this discussion offline after the class? I'd love to
Yes, sir.
explain to you in detail because theory, mathematical theory, I'm not interested in wasting everyone's time. And you are most welcome. We love to discuss those things.
Okay, sir. Thank you.
But I'll try to explain to you conceptually, which fits the bill here right now. I can explain. So what I'm saying, when we are running the OLS optimum least square method, what happened? As somebody was, I think Weber was asking, we were calculating the value of SE. You remember? When we were doing the F test
Yes, sir.
and we are doing T test. So F test is there for model and T test is for
Uh,
coefficients.
oh, yes. Okay.
Yes or no? This is
Yes,
there
sir.
for coefficient.
Yes, sir.
T test is for coefficient and F test for model. So what is happening? A common thing which we are estimating is common problem is sigma. And this is sigma is of the model.
Yes.
You are with me?
Yes, sir.
So what is happening when I'm running SE, calculating SE of whether coefficient or SE of model, what is happening? I have to make use of standard deviation of the model. Are you with me?
Yes, sir.
So what is happening when I have to calculate this and when whether I am doing the F test or I am doing the T test, why I am doing this so that I can calculate I can estimate whether my model is appropriate or not, my coefficient is appropriate or not. So this estimation of F or T needs sigma, and if sigma is not constant, are you with me? If sigma is subject to change
Yes.
with respect to x, then this calculation part will not work. It will give me varying impact. No? Are you with
Okay.
me? I
Yes, sir.
hope I have
Understood.
tried to answer you in the given time span.
Yes, sir. Understood.
Understood the point? So
Yes, sir.
just because my testing of significance of coefficient as well as model will be questionable, I will have different values of sigma which will not be constant in a given model itself. By model to model, it will vary that, which is pretty okay. But within the model, when you are finding this is changing, then I've got completely touchy-turvy situation. I can't handle it. Are you with me?
Yes, sir. Understood.
So just because I have to keep it constant, I have to ensure that my model is having the conditional variance. This is the variance which we are referring to. So this should be constant. If it is not, then I'm in a soup. I can't handle this situation. So OLS per se depends upon constant to variance concept. I hope point is clear.
Yes, sir.
But despite that, you can ask any other further questions of the class after this class also. I'm okay. I have no problem. Just send me WhatsApp. I'll fix a time and talk to you at later. I have no problems.
Thank you, sir.
Any other question? I would appreciate if you ask questions.
Sir, I want to ask a question.
Please go ahead.
If we look at you calculated in that Excel sheet, you calculated U for each of the observations. And
Perfect.
you just pointed out that the U is different for each of the observation. It is not the same, but you said that the variance of this values will remain constant, should remain
Conditional
constant.
variance. Conditional.
Condition. Okay, okay.
Conditional. Please pay attention. Variance can be straight away calculated. One sec. But when we say conditional variance, then we have to stop. We can't do that calculation in that simple way. But everything can be calculated. But what I'll do, I'll remove the x2. I'll have only one independent variable. If I have to show you, I'll do it. but I'll make it simple because as the number of independent variables increases, then permutations goes up. So I'll show you with the help of one, and I can prove my point, I can move on. But again, that's a lot of theory, which is not desired at this point of time, but if you are interested, I can take, no problem.
So coming to my question, so when I'm trying to use a model to estimate the value of the weight given the height and age, so I will be entering one value of height, I'll be getting one value of I'll be entering one value of age, and I'll be getting some value of weight, which will be weight cap. Then I'll have to add some u cap to get the actual weight. So that at that point of time, how will I estimate the value of u cap? If since u cap itself is varying.
Hold. Thing is that when we are having this model we have estimated, and we have done this whole discussion for the whole model. This is the model. These are the strengths and weaknesses of model. That job is done. Then this model can be put to use. Means somebody else, a new fellow will come. Let's say this model is made and given to people to use. Let's say some gym has got this equation with them in their system. It is there, and a new person come to the gym instructors and they check with the gym instructor, sir, what should be my appropriate weight? Can you suggest? Then the instructor will ask, what is your height and age? Suppose I have made a macro in Excel and I have keyed in height and age and I have got a value of Y. So that Y is the predicted value of Y. So I'm interested in making use of the model which I have made. Are you with me?
Okay. So does this mean that we will not be adding u cap then to the in the model?
Why? Because once we have made the model and tested the model, right now we are having this much discussion to explain to you that the model should not be made and forget. Rather, you have to report the strength and weaknesses of model using these 5-point summary. Once we have done, so okay, for a given model at a given point of time, this is the summary, and now let's use it. Why we are doing this whole exercise? Because we want to make a model for a certain use.
Okay.
Understood?
Yes,
One more
sir.
follow-up thing which you have not asked. I'll not stick to one value. I'll give you a range. Because when you are exploring the uncertain future, it is wrong to say just one value. Rather, it makes more sense to give you a range. Are you with me?
Yes, sir.
So I'll give you not a just value. I'll give you a range. I'm open to more questions. Please ask. Shoot. I want all of you to take part in discussion. If you're not clear, yeah, let me come back to the at least heteroscedasticity. I'll complete. Look at here. There is already a pair of, the hypothesis test of heteroscedasticity has the null of no heteroscedasticity. Are we together? I have to again go for testing of significance to establish whether my model is having the problem of heteroscedasticity or not. I need to test. And to test that, again, I have to go for testing of hypothesis. So my null for heteroscedasticity is going to be H naught is no heteroscedasticity. H alternate, yes, there is heteroscedasticity. You can check the language, no heteroscedasticity. Same thing is reported. Test of heteroscedasticity has null of no heteroscedasticity. So H not no heteroscedasticity. Class, are you with me?
Yes, sir.
I'm finding only a few of you are speaking. I appreciate if all of you ask and say you're not clear. Okay. So this is the, and I'll take you to Stata. In a Stata, there is a follow-up test. Once I have run this, then you have to stat command you have to write, remember stat and ht test, head test. And uh, just I'm missing some spelling. Is that correct? What is the problem? Okay. Now it is the value. Yeah. If you look at the value, let me repeat the whole thing. I may not estimate the standard coefficient. I straight away estimate, and then, yeah, I just missed out one more T, hit test. So this is the value of testing of hypothesis for testing of heteroscedasticity. And look at this, this is the p-value. Yeah. If I look at the p-value, I need to report both. I'll report it like this. The value 0.10. So I'll say value is 0.10. In bracket parenthesis, I'll again write down the p-value 0.75, 0.7538. So this is the way to report. Let me report it, then I'll complete the discussion. Degree of freedom, I'll just degree of freedom, these two things I'll cover. Testing of heteroscedasticity here. Value is 0.10, 0.10, bracket, I'll write down 0.75. So we'll go by our conventional approach to look at the testing of hypothesis. We have got the p-value, which is p-value in this situation is equal to 0.7538, which is less than 0.05 or more than 0.05.
More.
Which is obviously more than 0.05. Huh? More than. So we'll say that if I go by my simple old interpretation of any testing of hypothesis, if p-value is less than 0.05, reject the null. So right now it is not there. So we'll say we cannot reject the null. We do not have sufficient evidence to reject the null. Null cannot be rejected. Right now I'll say null cannot be rejected. So null cannot be rejected. So null has to be accepted. Language, we say that null cannot be rejected. So we have to consider it as if it has been accepted. So we'll say no heteroscedasticity assumption in the model cannot be rejected. So we'll report that model does not have problem of heteroscedasticity. Thus,
Yes.
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 Anyone else? After running the regression, we have to go for diagnostic testing. One of the tests we have done is testing of heteroscedasticity. And we have gone for writing this formula, E stat. This is post estimation test, head test. And we have got this, we have to cram E stat head test. And we have got this value. And we have looked at the p value. P value is more than 0.05. We'll say that null of no heteroscedasticity cannot be rejected. So conclusion is that model does not have problem of heteroscedasticity. As we have reported here in output, we will write here, we'll say model does not have problem or issue of, does not have issue of heteroscedasticity because p value of heteroscedasticity hypothesis testing hypothesis testing is insignificant. And that's it.
Sir,
Listening, yeah, please tell me.
yeah, sir, assuming that if in the model there was a problem of heteroscedasticity, so would we have to make some changes in the model, or we would just have
Yes,
to
yes,
mention
yes,
in?
yes. We have to make certain changes. We have to make certain changes. But first of all, are you clear with this? How
Yes,
to
sir.
check for heteroscedasticity? That is the important thing.
Yes, sir.
Other students, altogether, I have got 4 caselets to handle the regression analysis. We are doing first, so 3 more. So you will have cases of heteroscedasticity significant. At that time, we'll do the discussion. Right now, focus on important part, how to figure out whether heteroscedasticity problem is there or not. Corrective measures, we'll learn, that is simple. We'll learn for all the 3, practically for 2 at least, heteroscedasticity and autocorrelation. Don't you worry, there are methods. But there are some solutions, like you are suffering with some disease. So some solution is there, and beyond a point, there is no solution like that. So that type of solutions are there to handle the problem of heteroscedasticity. To some extent, we can handle. Beyond that, we have to, bear with the model limitation of model. We are supposed to report it and move on.
Okay, sir.
There is a method, suppose when you are running the this regression, then you can comma and robust, robust, just run robust test. And right now, when we run robust, then these significance, basically when we go for robust, what happened that the problem of heteroscedasticity and autocorrelation both at one go would have been taken care of, and the performance of the model would have been improved, keeping this in mind that the model is suffering from heteroscedasticity problem. So just because there is no problem, so no point of running the model with the robust estimation. But had there been problem of heteroscedasticity, we could have gone for estimating the model with this robust option. And robust option corrects the problem of heteroscedasticity and the problem of autocorrelation. But there should be a problem, then only when we need to apply the solution. Any other follow-up question? So let me just finish these 2 portions so that degree of freedom, when you look at this regression, you will find that degree of freedom is number of observation is clear 10. You can note down number of observations. So whatever is there, we can. For degree of freedom, calculate without robust. I think this model doesn't come when we run the ANOVA table doesn't come. Look at here. So when we have this normal regression analysis, then this number, please pay attention. You have to find out where the degree of freedom is. So this 7 is degree of freedom in this case. I can write down, I'll tell you the generic formula also. So generic formula is something like this for degree of freedom. The degree of freedom is equal to n minus k plus 1. Please note down what we are talking when we are saying n is total number of observations, and k is the number of independent variable. Independent. So if I put it the value number of observation 10, in our case, number of independent variables are 2. Actually, 1 we are adding because we are considering that we have got 3 parameters to estimate: beta 0, beta 1, beta 2. So number of independent variable will give me 2. 1 we have to add, because this signify the constant term. So we are estimating 3 coefficients: beta 0, beta 1, beta 2. That's why this formula of k plus 1. So this gives me 7. 7 I have said that 7 we are supposed to report. Statement extra. I strongly dislike to take more time, but it's okay. So I've calculated the value of degree of freedom. Degree of freedom will have some utility, don't you worry. There is no information which is being reported has got no value. Everything has got some value or the other. So with this, we have come to an end to today's class. I hope class was clear. Those who have got any problems, small or big, please approach to me. Next week again we'll meet and we'll take it further and we'll try to move slightly faster in next classes so that we finish our regression analysis. I appreciate your discussion. I'll appreciate more if you ask more questions. So thank you very much. I'm closing it.
Thank you, sir.
Thank you, sir.